And I just decided that the best way to do laundry was to teach everybody in my house how to do their own laundry, and be only responsible for my own.
Works.
By the time the kids hit first grade, they were doing their own laundry. Not having it. No reason I should be doing your laundry, you're
Oh,
capable person. It's not that hard.
So I don't know why the document camera is not connecting here, but I will talk to the IT guys, they will fix it. But I'll be, did you see the notes? I scanned the notes and then I posted it to Moodle. So you need to refer to them. And then any question on the homeworks? Anything? So you can check this one. It's like the one which you have online. You can check it. Questions. Yeah. Okay. Is it time to start? Yeah. So last time we were looking at the row reduction. Do you have any question on that? But we'll still do a lot of examples on the set. Okay, so let's look at elementary row operation. So when we were doing the row reduction method, then I introduced R as the row. So we can say Ri, and then if you want to interchange with Rj. So if this is the formula for interchanging, like bringing, let's say, the first row to second, like that. So you interchange the rows. So this is interchange the ith row and the jth row, where I is not equals to j. So interchange. So we can say here we recall that Ri is ith row in a matrix. Ri is the ith row in a matrix. So that is interchanging the rows. So you can interchange, I should not be equals to j. So the first row is always not equals to the second row. Okay, so I mean, like the example we had, if the first row has 0 entry in the first entry is 0, and the second row the first entry is 0, then you don't have to interchange it. They're similar. So you need to look for the one which is not the same. It's not the same. Okay, another one is if we have the Ri, the ith row, if you want to get the new I row, whereby you multiply this by a constant Ri. So to get a new Ri, you can also still multiply by a constant. You can multiply by a constant. So this is a new Ri. This is a new Ri. So you interchange with Rj. So this is a new Ri. You multiply by the constant. Where? So this is multiply every entry in the ith row by k, where k is not equals to 0, where k is not equals to 0. The last one, Ri, to get the new Ri, you can say Ri plus C multiplied by Rj, plus C multiplied by Rj. So look at this. This is what we were doing. This is what I was showing you yesterday. So let's say this one is row 3. Then here should be row 3. Okay. So Ri here, Ri here, and then the other one can be different. So make sure you remember this. So if you want to get the new Ri here, then Ri is the same as Ri plus C multiplied by Rj. So this is replace the ith row with the sum of itself and C times the jth row where I is not equals to j, where I is not equal to j. So those are the 3 elementary row operations. Okay, so if we have the elementary row operation here, and then the inverse operation. So if we have the first elementary operation by interchanging Rj, where I is not equals to j, then the inverse is the same, Ri and j. So the inverse are the same. Now, if you multiply by a constant Ri to get a new Ri, you say Rk by Ri, where k is not equals to 0. Then the inverse is Ri, where you multiply by 1 over k Ri. So that would be the inverse. Now, if the last one there, Ri, to get a new Ri plus C Rj, where I is not equals to j, then the inverse Ri is Ri minus C Rj. So that is the inverse. So you want to bring it back to the new one, to the same operation that we had. That is the inverse. That is the inverse. So let's look at an example. Example number 6. Example 6. Find an elementary row operation that transforms the first matrix M1 into the second matrix M2, and then the inverse operation that transforms M2 into M1. So into M1. So if we have the first matrix here, A, whereby this matrix is 0 minus 2, 5, 1, 4 minus 7, 3 minus 1, and 6. So if this is our M1 and our M2 is 1, 4 minus 7, 0 minus 2, 5, 3 minus 1, 6, 3 minus 1, 6. So what is happening here? So if you look at the, so this is M1 to M2. So transform it from M1 to M2. So what has happened here from M1 to M2?
Just interchanging.
So we just interchange. So so M1 together new M2. So it is R1 interchange with what? R2. R1 interchange with R2. So what is the inverse? So the inverse is M2 to M1. We are doing the same. So it is R1 interchange with what? R2. Interchange with R2. Okay, another example, B. We have this matrix 1, 3 minus 4, 0 minus 2, 6, 0 minus 5, 9. And then our M2 is 1, 3 minus 4, 0, 1 minus 3, and then 0 minus 5 and 9. So what happens with M1 to M2 and what happens from M2 to M1? So M1 to M2. So the first row is the same as this first row in M2. So what have we done to the second row there?
So I had to multiply that constant in half.
So it is
Right.
from our new R2, right? Our new R2 is we multiply by -1 over 2 R2, right? That's 1 over 2 R2. Now, if you want to go back here, so what will we do? So to get our new R2, which is here, then we do what? We multiply by what? We multiply by -2 R2. By -2 R2. So that is simple. Okay, number C. If we have this matrix 1, 2 minus 5, 0, 0, 1 minus 3 minus 2, and then 0 minus 3, 9, 5. And then the next one is 1, 2 minus 5, 0, 0, 1 minus 3 and minus 2, then 0, 0, 0 and minus 1. So what is happening from M1 to M2, and then what happens from M2 to M1? So the first row there, it is the same. Second row is the same. So the operation is taking place on the third row. So what have we done in the third? So to get the new R3 here,
3 R2.
so it is R3, right? So it is R3, and then we do what? We add
3 R2.
R3, R2. Yes, we add the R2. So what is the inverse to get the new R3 there? Then we do what? It is R3 minus 3 R2. 3 R2. So those are the elementary row operations. The elementary row operations. Okay, let's look at example number 7. Find all solutions of the following linear system if they exist. If they exist. If they exist. So if you have this linear system, x1 minus 3x2 plus 4x3 equals minus 4, 3x1 minus 7x2 plus 7x3 equals minus 8, and then minus 4x1 plus 6x2 minus x3 equals to 7. 7. So determine whether this has a solution or not. So how can we know whether this has a solution or not? So we can use the what? The row reduction method. The row reduction method. So first of all, we write the coefficient matrix. So our coefficient matrix are the coefficients here. And then the augmented matrix, which is you add the constant terms there. So our coefficient matrix here will be the solution. Our coefficient matrix will be 1 minus 3, 4, 3 minus 7, 7, and then minus 4, 6, and then minus 1. And then we do what? We write the augmented matrix minus 4, minus 8, and 7. Then we use the elementary row operations to reduce this, So here, since this one is not 0, then we don't have to use the first elementary row operation. So we want to make this, that, and that to be what? To be zeros. So we want to make this to be 0, we want to make this to be 0, and then this one to be 0. So let's start from this. So here we want to get the new R2 using R1. So it is R2, and then we do what? We minus 3 R1. Minus 3 R1. Again, we are also using, you can also reduce this to 0, the last one, to get the new R3. Then it is R3, and then plus what? 4 R1. It's 4 R1. That is the last one there. So here you retain the first row, minus 3, 4, and minus 4. And then here now, that is what you now add, subtract 3. So this is 0, minus 7. So minus 7, here will be plus, right? So plus 9 is what? Is giving us 2. 7 minus 12 is giving us minus 5. Minus 8 plus 12. Minus 8 plus 12 is giving us 4. Then the last one here, R3. So minus 4 plus 4 is giving us 0. 6 minus 12 is giving us what? 6 minus 12 is minus 6. And then minus 1 plus 15 is giving, plus 16, sorry, is giving us 15 there. And then 7 minus 16 is what? It's minus 9. It's minus 9. Okay, right? Now we want to make this one to be 0 here. We want to make this to be 0. So to get the new R3, then it is R3, R3 plus 3R, R2, R3 plus 3, R2, R3 plus 3, R2. Okay, so here, so we retain the first one, minus 1, minus 3, 4, and minus 4, then 0, 2, minus 5, and 4, and then here it is 0, minus 6 plus 6 is 0, 15 minus 15 would give us 0, and then minus 9 plus 12 is giving us 3. It's giving us 3. Okay, so that is what you get. Now, if you look at this, since this one is x1, this is x2, and this one is x3, right? So if you look at the last row here, the last row here, of course, this is what? So therefore, if this is 0, and we have a number here, then that means we don't have a solution, right? So we don't have a solution. So therefore, we can note that the third row in the last matrix is equivalent to, so the last row here is equivalent to 0x1 plus 0x2 plus 0x3 equals to what? Equals to 0. Equivalent to that. So therefore, which cannot do what? Which cannot hold for any x1, x2, and x3. And therefore, the linear system is inconsistent. The linear system is inconsistent. So the linear system. So we don't have the solution there. Okay, any question after that? So let's look at the remark. Am I going fast? Okay. If the augmented matrix of a linear system contains a row in which the last entry is non-zero and all other entries are zeros, then the linear system is inconsistent. The linear system is inconsistent. Such a row in the augmented matrix of a linear system can be called a contradictory. Contradictory row. So the last row, whereby the last entry is not zero and the others are zero, then it is a contradictory contradictory. So the linear system is inconsistent. Inconsistent. Okay, let's look at example 8. Example number 8. The following matrix represents the augmented matrix of some linear system. Find all the possible values for the parameter H such that the linear system is consistent. Such that the linear system is consistent. So if we have this augmented matrix as 1H minus 2, and then minus 2, 4, and 6. So how can we determine the values of H that can make this linear system to be consistent? So the solution. So you reduce this matrix. So let's reduce this one. So we want to make this minus 2 to be 0. So how will you reduce it? To get the new R2, then it is R2 plus 2 minus 1. So we retain 1H minus 2. And then here will be 0. Then here will be 4 plus 1. So 4 plus 2H. So 4 plus 2H. And then the last one is 6 minus 4, which will give us 2. Which will give us 2. Now, for this linear system to be consistent, then what will be the value of H? So it means that this one should not be equal to 1. So it means that for this one to be consistent, then 4 plus 2H is not equal to 0. Or take these ones to the other side. So take all this to the other side. So 2H should not be equal to minus 4. And then H should not be equal to what? Minus 2. H should not be equal to minus 2. For it to be consistent, H should not be equal to minus 2. That means this should not be equal to 0. All right, so let's now come to the next section, which is 1.2. 1.2. And this is the row reduction and echelon forms. Row reduction and echelon forms. So our first section will be the echelon form matrices and reduced echelon form matrices. Echelon form matrices and reduced echelon form matrices. Okay, let's start from the first one, which is the echelon form matrices. So what we were just doing is the echelon form. So when we make the others, the bottom one and the top one to be zeros, then that is the reduced echelon form. So we can say an echelon form matrix is a matrix of the form. So it is a matrix of the form. So we can actually write this matrix. So we can put this one to be like that, and then the others to be the star. And then all these are zeros. That one to be like that. The next one. This is still star. Star. So you can continue like that up to maybe the last one there. And then start. Okay. Oh, zeros. So basically, the leading diagonal here can be any number. So this can be any number here. So it can also be 0. So any number here and along the leading diagonal should be some values. So this is the main diagonal here. So any values below this should be zeros. So that is the echelon form of that matrix. Just like what we did here. So basically, this one is in echelon form. So this is in echelon form. Echelon form. So this is where, number one, all the non-zero rows are above the 0 rows. All the non-zero rows are above the 0 rows. Number two, the leading entry, which we can say that leading entry is where it is in the main diagonal in a non-zero row is strictly to the right of the leading entry in any row above this non-zero row. Okay. So looking at this is actually strictly to the right. So it is to the right. So this one, the other value here should be this, and the others are zeros. Should be this, and the others are zeros. Okay. For example, okay, before that, can write in an echelon form matrix, the position of a leading entry is called the pivot position. The pivot position. And a column that contains a pivot position is called a pivot column. So for this, if we have the leading, this entry here, this is the pivot position. This is also a pivot position. So the columns which have the pivot positions, they call them pivot columns. Pivot columns. Pivot columns. So for example, we have this matrix, 1, 2, -5, -6, 0, -5, 0, -1, -6, -3, 0, 2, 0, 0, 0, 0, 5, and 0, and then 0, 0, 0, 0, 0, 0. We have that matrix like that. So what is, so this is the reduced, sorry, this is the echelon form matrix, because these are zeros, this is 0 here, and then this is 0 down here. So we said all the non-zero rows are above the 0 rows, and then the leading entry in a non-zero row is strictly to the right. So this is our pivot position here. This is our pivot position. See, so this cannot be our pivot position. So we look for another one, and then this is our pivot position there. Okay. Pivot position. So we don't have any other one here. So our pivot positions are at the first row, the second row, and what? And 1, 2, 3, 4, 5, and the fifth row. And therefore, the first, the second, and the fifth are the pivot columns. So those are pivot columns. Any question up to that? So to get the echelon form of the matrix, then we actually use the elementary row operations. So to get the echelon form of the matrix, we use the elementary row operations. So you can use as many elementary row operations as you can until you get zeros here. The zeros and also the zeros. Okay. Okay, let's now see how we can solve using the elementary row operations to get the echelon form of the matrix. So example number 2. So this was example number 1. So example number 2. Find 2 different echelon forms for the following matrix. Cycle the pivot positions and find the pivot columns in the obtained echelon form matrices. So you have this matrix here, 1, 3, 5, and 7, and 3, 5, 7, and 9, and 5, 7, 9, and 1. So we have 2 different kind of echelon form. Okay, so let's reduce this matrix. So let's reduce this matrix to echelon form. So we can use finitely many number of elementary row operations here. So when we reduce this matrix, so we want to reduce this to 0, this to 0, and this one to 0. So let's start from the second row. To get a new R2, then it is R2 minus 3 R1. To get a new R3, then it is R3 minus 5 R1. So therefore, when you reduce this, the first row is maintained. So the second one is 3 minus that is 0. 5 minus 9 is minus 4. 7 minus 15 is minus 8. Then 9 minus 21 is minus 12. Second one here, the new R3, this is 0. And then 7 minus 15 is minus 8. 9 minus 25 is minus 16. And then 1 minus 35 is minus 34. Minus 34. So then we can also reduce this. So to get the new R3, then it is R3. R3, what do you do here? Minus, right?
R2.
Minus 2 R2. Minus 2 R2. So the first one is retained. Second one is retained. And then finally, this is 0. This is 0. The next one is what? 0, right? And then the last one is negative 10. So that is our first one. So therefore, our pivot position is here, and what? So those are our pivot positions. Our pivot position. Then we can still do something. Yeah, we can still do one. Reduce again this one by dividing by 1. By negative 4. And this one by 1 over negative 1 over 10. So we can still reduce this matrix. So definitely we have our pivot positions here. You cycle them there. So those are our pivot positions. So
This is not an argument.
It is. So this is, if you close that one, it's a 3 by 3.
It's inconsistent, isn't it? Because
Yeah,
the
yeah.
last one is-
Yes, it is. It is inconsistent. Definitely it is inconsistent. So, but we are just looking for the pivot position and the pivot column. Yeah. Okay, so we can still reduce this one again by getting the new R2 here by multiplying by negative 1 over 4 R2. You can still get the new R3 there by multiplying by negative 1 over 10 R3. And therefore what you get is 1, 3, 5, and 7, 0, 1, 2, and 3, and then 0, 0, 0, and 1. So our new other pivot positions are here. Pivot positions and the pivot columns are where the pivot positions are. So this is our pivot column, this one, and the one. So this is our pivot columns. Okay. Any question up to that? So you can still cycle after getting the pivot positions here, you can still cycle the pivot columns and the pivot positions in this matrix here. So we actually found our pivot position here, our pivot position here, and our pivot position in the last one there. So we found our pivot position here, here, and the last one. Okay. All right. Now, what about the reduced echelon form matrices? The reduced echelon form matrices. So what do you do here? So you follow the steps that we had in the echelon form to the next one here now. And to the next one. So our third, so we had the first one and the second one, which was the first and the second one here, right? So our third will now be the leading entry in every non-zero row is 1. The leading entry in the non-zero rows should be 1. Just like this. So you make this one to be 1. Okay. You make those ones to be 1. Then, number 4, there is exactly 1 non-zero entry in every pivot columns. That is exactly 1 non-zero entry in the pivot columns. So the pivot columns should not be having this 0 entries. Like, for example, if we have this matrix, yeah, which is 1, 0, minus 11, minus 12, 0, and minus 1, 0, 1, 6, 3, 0, and minus 2, then 0, 0, 0, 0, 1, and 0, and then 0, 0, 0, 0, 0, and then 0 there. So this is example 4.
Move that up a little bit.
That is example number 4. So this is actually a reduced echelon form, because here, this is our pivot position, this is our pivot position, and this one is our pivot position. Okay, our pivot position. Then, and they are also what? All are 1s. They are all 1. So they are all 1. So above those leading entries or pivot positions, they should be 0s. So above that, they should be 0s. For this one to be reduced echelon form, so anything above the pivot position should be. So therefore, this is a reduced echelon form. Since above this pivot position is 0, of course, this is 1, 0s, and then this is 1 and 0 above and 1 over there. So then you can say the following. matrix is a reduced echelon form matrix. Reduced echelon form matrix. 1 hour, 15 minutes is a lot. Okay. So what are the procedures on how to get the reduced echelon form of the matrix? So 1.4 procedure for finding the reduced echelon form of a matrix. So number one, from the first row to the last row, eliminate all non-zero entries below every pivot position. That's the first one. From the first row to the last, eliminate all the non-zero entries below every pivot position. Number two, reduce the leading entry in every non-zero row to 1 by rescaling all entries in this row. And then number 3, from the last row to the first row, eliminates all the non-zero entries above every position. So that is what I just said. Okay. Now let's look at an example, and we will do the same example that we just had here. So we just continue from where we left. So example number 5. Find the reduced echelon form for the matrix in example number 2. So we have reduced this matrix to echelon form. So we have reduced this matrix to echelon form. So our echelon form of this matrix we found as 1, 3, 5, and 7, and then 0, 1, 2, and 3, and then 0, 0, 0, and 1. So that is our echelon form of that matrix, right? Now since the pivot, so the first step, the second one is already done. So the leading, the pivot positions that are ones. So this is 1, this is 1, this is Now, we want to now, from the last row to the first row, eliminate. So you actually start from the last to the first row. So coming back. So you eliminate this two zeros here. Eliminate this one. So starting from the last row. Do not start from the first one. So start from the last as you go back. So you go. I think since you're doing engineering, I think there is something we call back propagation. What? Are you doing something like back propagation?
There's reverse engineering. That's working backwards.
Yeah,
Deconstruct something that was already made.
yeah, you do it back.
Yeah.
Okay, so to get now, you can start from the second one or the first one there, it doesn't matter. So you can start from the second one. To get a new R2, we want to make this one to be 0, this one to be 0. So to get a new R2, then it is R2, and then minus 3, R3, minus 3, R3. And then to get a new R1, since we want to make this 7 to be 0, then it is R1 minus 7, R3, minus 7, R3. Okay. So then what we get here is, so since this is, so we can start actually from the first one here. So 1 and 0, this is still 1, 3 and 0, this is still 3, 5 and 0, this is still 5, and then 7 minus 7, that will be 0. 0, and then 1, 2, and 0 there, and then 0, 0, 0, and 1. Okay. Then now we want to make this one to be 0. So to get a new R1, then it is R1 minus 3, R2. And then we get 1. So this is 1. 3 minus 3 is 0. 5 minus 6. 5 minus 6 is minus 1. And then 0 minus 0 is 0. And then 0, 1, 2, 0. Then 0, 0, 0, and then 1. So this is now to reduce epsilon 4. So this is the reduce. Any question after that? Now, so after reaching this point, then we can now use this, which reduce echelon form, to now find the solution of the system. So we now find the solution of the system. So basically, yeah, is there any solution? Yeah. So there's some solution. So there's no solution. So if the final position was here and then the other one is 0, then there could be a solution. Okay. So in this case, if you want to get a solution here, if there was, let's say, 1 here and maybe 0 here, so it means x1 is 0, and then here x2 and 2x2, x3 is close to 0, like that. Okay, that is how you can get a solution. Okay, now let's count the second section here, which is the solution sets of a linear system. The solution set of a linear system. So let's start from the basic and free variables. basic and the free variables. Okay, a variable in a linear system is called a basic variable if the column corresponding to this variable in the associated augmented matrix is a pivot. So just like this. So if here we have the pivot position, here we have the pivot position, and here we have the pivot. Let's not do this. Let's use this. Since this is the x1, x2, these are three variables here. In this case, where there is a pivot position, then that is where we have the basic, that is basic variable. So here, if this is x1 and this is x2 and this one is x3, this is a constant term, then our x1 here is our basic variable and our x2 here is our basic variable. But where there is no pivot position, then it now becomes the free variable. So in this case, our x3 is our free variable. So then, otherwise, the variable is called the free variable. Otherwise, the variable is called the free. Any question? So the procedure of solving the linear system is just the same as how to get the reduced echelon form. So I don't have to. You can, if you have the textbook, then you can look at 2.2, the row reduction method for solving linear systems. So there are like six ways of doing that. So we'll just do an example on this. Let's look at example number 6. Use the row reduction method to find all the solutions of each linear system. Number A, x1 minus 4x2 plus 7x3 equals to 1. 3x2 minus 5x3 equals minus 3. And then minus 2x1 plus 5x2 minus 8x3 equals to 1. So let's solve this. Let's solve this using the row reduction method. So the first step here is solution. So the first step is to write the augmented. We already know what is coefficient matrix. You just add that one. You get the augmented matrix. So write the augmented matrix of this. So which is 1 minus 4, 7, and 1. 0, 3, minus 5, minus 3, and then minus 2, 5, minus 8, 1. So that is the first step, right there. And then now reduce to echelon form. So you start from echelon form. So we already have this as 0. So we want to make this as 0 and this one as 0. So our new R3 will be R3 plus 2 R1, which is 1 minus 4, 7, 1, 0, 3, minus 5, minus 3, and then 0, then 5, 5, 5, 5 minus 8. This is giving us 3. Minus 3, sorry. Minus 8 plus 14 is 6, and then 1 plus 2 is 3. Then now we want to make this one to be 0. So our new R3 will now be R3 plus R2. So you get 1 minus 4, 7, and 1, 0, 3, minus 5, minus 3, and then 0, 0. So 6 is 1, 3 is 0. So from there, that is not what the last row is not contradictory, right? So this is not contradictory. So we get a solution there. Now, so we have the pivot positions. So we have our pivot position here, pivot position here, and the pivot position there. So we now come to the reduce echelon form. Reduce echelon form. So starting from the bottom, going up. So we want to make these ones to be zeros, and this one to be 0. Okay. Okay. So here, to get a new R1, since we want to make this 7 to be 0, then it is. So before that, you need to make this one to be 1. Okay. It is already 1. So if it was not 1, you need to make it to be 1. Okay. Yep. So to get a new R1, so R1 minus 7 R3. And then to get a new R2, then it is R2 plus 5 R3. So what we get there is 1 minus 4, then 7 minus 7, there is 0. 7 minus 0 is 7 there, right? And then 0. And then we have our 3. And then minus 5 plus 5, there is 0. And then minus 3 plus 0 there is minus 3. Then 0, 0, 1, 0. Okay. Now, you do what? What is the next step? What is the next step?
3 to 0.
Yes. So what is the next step?
Make the pivot position just not a 1, a 1.
Yeah. So you
Scale
make this
it to
one
a
to
1.
be, you make this one to be 1. So you divide by 1, 3. So the next step here, to get a new R2, then it is 1 over 3 R2. So which is 1 minus 4, 0, and 7. 0, 1,
I'm sorry.
0.
How did we get the 7 at the top right corner?
Oh, there's,
Because.
I think it's supposed to be a one.
Oh.
It's supposed to be a
I'm
1.
doing my own things, huh? So it is 1. So it should be 1. Yep. Mhm. So minus 1 and then 0, 0, 1 and 0. Then now we reduce that minus 4 up there to be 1, to be 0. So to get a new R1, then it is R1 plus 4 at 2. So which we get, so 1, 0, 0. So 1 and this one. So 1 plus 1 minus 12, which is what?
1 minus 4, because that's the next one over.
Yeah, I think I'm tired. So it's here. So 1 minus 4, which is minus 3. And then 0, 1, 0. And then minus 1, and 0, 0, 1, and 1. There. Okay.
There's it.
0.
What is the time? Oh, we have 5 minutes.
Call it a day.
Okay. Now, looking at that, so looking at that now, what we can see here is, so we have our basic variables. As what? Basic variables there as x1, x2, and what? x3. So 3 variables. None. So we don't have any free variables there. So then our new linear system there will now be x1 equals to what? Minus 3. x2 equals to minus 1. And x3 equals to 0. So therefore, our solution set, which is, we can name this one as x, is equals to x1, x2, x3, which is equals to minus 3, and minus 1, and 0. So that is our solution set. Any question up to that? Okay, so let me give you, maybe you can try this one at home, and then if it is difficult, we can do it when I meet. So we have this x1 minus 7x2 plus 6x4 equals 5, x3 minus 2x4 equals minus 3, then minus x1 plus 7x2 minus 4x3 plus 2x4 equals to 7. So when we meet next time, we will see that if you look at the number of variables here, they are more than the number of linear systems. So basically, if the number of variables there are more than the system, the linear system there, then basically we'll have the free variables. So we have the free variables. So our solution there, what you get is, so we'll come and see this one when we meet. So what you should get is, okay, we'll just come and see it when we meet. Right, I will post some of the questions for your homework.
So far, my book lines up with that one, so.
Yeah, so if it's lining up, you're good. Is yours okay?
It was way cheaper.
I will report you guys. If you want it online, I will report you.
Thanks, Kip. I'm good on.
All right, see you
tomorrow.
Mhm. All right, see you.